All right, guys. So in this video, we are going to talk about something that might be new for some of you guys, even if you've learned a bunch about polynomial functions last year in Algebra 2. I know when I had students in pre-calculus last year, some of them were like, oh yeah, this is a review until we got to this point. So we're going to talk about something in this video called the rational root theorem. It is not a whole lot new from what we were talking about last video that I made about graphing with synthetic division. However, there's a little bit of legwork at the beginning. We're really going to be testing a bunch of things and looking for essentially a remainder of zero. And once we get a remainder of zero, that's what we're looking for, and then we can progress through the problem from there. But before we do that, and we'll do a few different examples here in this video, and then I will have some practice for you guys to try tomorrow during class. So I'm not going to put any practice problems in the OneNote for today. You can just watch the video and then you're done for today. But tomorrow in class, we will work on, or there will be a worksheet that you can try for practice. Okay, so let's define this. What is the rational root theorem? Okay, so the rational root theorem, what it does is it tells us, all possible, okay, but not necessarily actual, rational roots. And all we mean by rational is no crazy decimals. Okay, so not a number like pi or the square root of something that's not a perfect square, but anything that's just a normal fraction or just a normal number that's not a fraction, we can get in terms of a rational root. So it tells us all possible rational roots of a polynomial function. Okay. All right, and the way that we find all these possible rational roots is we use this right here. We do x equals plus or minus. This is not necessarily going to make sense right now, but we'll do some examples, obviously, and hopefully this will make more sense as we go. Plus or minus all of the factors of the constant divided by all of the factors of the leading coefficient. Sorry, write that again. The leading coefficient of highest degree. Okay. So we'll take the number at the end, that's the constant. We'll list out all of its factors, and then we'll take the number at the beginning, that's the leading coefficient of highest degree. We'll list out all of those factors. I'll kind of talk to you about how that develops a list. We don't need to list them all out, other than just writing what you see right here. But it develops a list, and then what we're going to do is we're going to test all of the things that we can see in that list, and we're searching for a remainder of zero when we use synthetic division. And so you'll get the hang of this process as we go. Let's go ahead and jump right into an example. We'll probably do two shorter examples and then one longer example at the end here, just to kind of get you guys an idea of what we're looking for on these problems. So let's try this. We're going to go f of x equals, let's try x cubed minus 19x minus 30. Okay. All right. So the first thing that I want us to do here, and we use the rational root theorem if it's not a quadratic and it's not something that we can factor by grouping. And this is not a quadratic, and I can't even try to use grouping because there's not an even number of terms here. So the first thing that I want us to do is let's write out all the possible rational roots of this function. Okay. So what I mean by that is we're going to list out all the factors of 30. Okay, that's the factors of the constant. That's going to go up on top. So it's going to be 1, 2, 3, 5, 6, 10, 15, and 30. And then on the bottom, we're going to list out all of the factors of the leading coefficient of highest degree. Well, that's easy because there's just a 1 out here, and the only possible factors of 1 are 1. And so what we've done right here is we've created a list, and this is all you have to write down. But just to kind of show you how to read this list, it's like plus or minus 1 divided by 1, so that's 1. And then plus or minus 2 divided by 1, so that's 2. And then plus or minus 3 divided by 1, that's 3, and so on and so forth. And then if there was another number in here, like, I don't know, a 5, well, then we would have all of these numbers, but then we'd also have like plus or minus 1/5, and plus or minus 2/5, and plus or minus 3/5, and so on and so forth. Okay, so I'll kind of talk about that as we go, but you don't need to write all that out. As long as you write down this fraction, and you're starting to get an idea of what you could get, that's what I'm looking for. Now, it might seem kind of daunting because what we're going to do is we're going to take this function and we're going to try to divide it by different factors that I can get from this list and see if I get a remainder of 0. But the easiest way to do this is to think about this systematically and formulaically, because a lot of students are like, well, where am I supposed to start? Am I supposed to start with x equals 15? Do I start with x equals negative 10? Well, my advice is going to be, let's try x minus 1 first. Okay. So what I'm going to do, because no matter what, every single function is going to have a 1 and a 1 right here, which means you can test x equals 1 and x equals negative 1. So by testing x minus 1, I'm trying to see, is x equals 1 a solution or a root of that function? And so no matter what, you're going to be able to try x minus 1 and x plus 1. So if x minus 1 doesn't work, I'm going to encourage you to try x plus 1 next. Okay. If x plus 1 doesn't work, then try the next easiest thing to try in the list. In this case, the next easiest thing to try in the list would be x minus 2. Okay, but I'm going to put a little note here. I'll say only if possible should you try x minus 2. So for example, if you had this, f of x equals x cubed minus 5x minus 9. Well, if I was making a list for this one, it would be plus or minus 1, 3, 9, because those are all the factors of 9, divided by 1. So you could try x minus 2 with this, but I can guarantee you x minus 2 won't work since x equals 2 is not something that I can get from this list right here. Okay, so I should only try things if it happens in this list, but I want to go systematically here, and I can try x minus 1, then I can try x plus 1, then I can try x minus 2 if possible, then I can try x plus 2, and then I can try x minus 3, and then I can try x plus 3. The only way that this is going to work as a root of the function is if, when I do my synthetic division, I get a remainder of 0. Okay, so I'll put a little note here. I am looking for a remainder of 0 with synthetic division. If I do not get a remainder of 0 with synthetic division, then I know that one doesn't work and I can move on to the next one. Okay? So let's begin with this problem. Okay? Here's what I'm going to do. I'm going to start by trying x minus 1. So I'm going to take this function, f of x, and I'm going to divide it by x minus 1, which means I need to put a 1 in the box, and then I'm going to list my coefficients out across the top. Notice that I skip x squared right here. So this is going to be 1x cubed, 0x squared, negative 19x, and then negative 30. Okay, and let's try it. Okay, I'm going to not talk too much here as I try the synthetic division. So 1, I'm not even going to write the plus in the middle here. All right, when I get to this step, if I can tell that I don't get a remainder of 0, then that doesn't work. Okay, so x minus 1 is not a factor of this function because when I divide by it, I don't get a remainder of 0, which means I don't care about it. I'm going to move on to the next thing. So the next thing that I'm going to try is x plus 1. Okay, so let's see what happens when I try x plus 1. Okay, well, unfortunately, that doesn't work either. Okay, tried x plus 1. Once again, I did not get a remainder of 0. So let's move to the next thing in the list. Well, the next thing in the list is 2 divided by 1. So I'm going to try that. So we'll try x minus 2. You could try x plus 2 first. It doesn't matter which one you go with. I just like to have positive numbers in the box if possible. So let's try it. So once again, 1, 0, negative 19, negative 30. And you can kind of see why being good at synthetic division is going to be really important here, because you might have to try this a bunch of times, but it doesn't take very long. And so the quicker you get at your synthetic division, the better you're going to be. Now, check this out. We're pretty close right here, but unfortunately, negative 30 plus negative 30 doesn't give me 0. Okay, that would only give me a 0 if that was a positive 30, but it does seem like we're getting closer. So maybe if we try x plus 2, maybe this will work. Let's try it. 1, 0, negative 19, then negative 30. Let's see what happens. So 1, -2. Okay, 0 plus -2 is -2. We go 4, -15. And fortunately for us, I get a remainder of 0, which is what I wanted. Yeah, okay? So that's what I'm searching for here, is I'm looking to see which possible rational root, when I divide by the factor that would cause it, gives me a remainder of 0. And in this case, I figured out that x minus 2 works. So at this point, I always say, okay, let's stop. Let's collect our thoughts a little bit. Let's see where we're at in the problem. So here's what I've figured out thus far. Okay, I've figured out that when I divide this function by x plus 2, it gives me a remainder of 0. So I want to look at what's left over when I do this. And this was x cubed. So this is going to go down to x squared. So this is going to be x squared minus 2x minus 15. Okay. All right. Remember, as I've mentioned, the whole idea of this is to get ourselves down to a quadratic. Once I get myself down to a quadratic, I'm feeling pretty good about things. Sorry. And so let's see if we can finish the factoring here, and then we can graph it, and the graphing shouldn't take very long. So I'd be looking for, I'm going to put an x and an x. I'm looking for factors of 1 times -15, so that's -15. That add up to -2. Those two numbers would be -5 and 3. And I do not have to divide anything out of this because I already have x times x, which is x squared. So this right here is the completely factored form of this function. So this is kind of cool because we took something that we have no idea how to factor, and without me giving you any information at all, except for just what is the rational root theorem, we tested with synthetic division, we figured out what worked, and then from there we got ourselves to a quadratic, and we could factor that quadratic. Okay. Last but not least, we can graph this thing. Let's see, multiplicity, 1, 1, 1. Add those all together, I get 3. This is positive. That matches up exactly with what I saw at the beginning of the problem, 3 and positive. So I'm feeling pretty good about that. Make sure we don't lose track of anything. That is odd and positive. That's down, up. Okay, if I think about x-intercepts, and you'll notice this last part of the graphing gets very redundant because it hasn't changed at all for the entire unit. So I'm always surprised when students still don't know how to graph at the end because I'm like, well, we've been doing this for a while now. So x-intercepts, we've got -2, 5, and -3. Okay, and we'll sketch in our graph. We've got -3, -2, and 5, putting these things in order. We are down on the left, up on the right. There are no repeat factors, so everything is to the first power here. And we will finish here by just going straight through at each one of these x-intercepts. And here's what my graph's going to look like. Okay. Doctor just came in, so I'm going to stop this video here for a moment, and I will make another one to finish up our last two examples for the day. Thanks. Bye.